Hello, I'm Conor Most.
And I'm Yojar, and this is our Aero 320 project.
Our project involves modeling the behavior of rattlesnake egg magnets in a fixed reference frame. We do this by holding one magnet fixed and modeling the rotation and oscillations of the other magnet.
The assumptions we make for our project are no air resistance, a constant magnetic field, and rotation only about a fixed z-axis.
The following situation is a basis for our project. Similar to the pendulums we studied in class, we are interested in modeling the system's angular displacement and angular velocity. Thus, we chose states of theta and theta dot. We then use Euler's laws to arrive at our equations of motion.
Other important parameters to note are m, the mass of one magnet, l, the distance from the rotation axis to the pole, b, the strength of the magnetic field of the magnets, p, the strength of a magnetic pole, and c, the frictional damping constant.
For our solution procedure, we first summed moments about the z-axis in accordance with Euler's laws. We then expanded the expression and made any necessary simplifications. Once the equations of motion were found, we converted to a state space representation. As you can see, the system is nonlinear. This is due to the sine theta term that arises from the magnetic torque cross product. Thus, we were forced to linearize. First, we found the equilibrium points x star, which ended up being 0, 0, and pi 0. We then found the Jacobian, and then we evaluated this Jacobian at x star to arrive at our linearized system. We then used two methods to solve the system.
The first was ODE 4.5 on MATLAB. This first graph depicts a displacement of 90 degrees and no initial angular velocity. The second graph shows the same 90 degrees displacement, but also includes an initial angular velocity. Another method of solving the system was using Simulink. This block diagram represents our system and makes use of a P controller, since the only things controlling the system are two proportional gains affecting theta and theta dot.
In summary, our system is a pair of damped oscillating magnets. Our governing equation of motion is theta double dot minus c over ml squared theta dot minus pb over ml theta equals 0. Our system is continuous.
The inputs of our system are the initial angular displacement and angular velocities of the top magnet, while the outputs are the angular displacement and angular velocity at time t of the same magnet. Our system uses negative feedback.
Our system uses a P controller with two proportional gains. Important metrics include settling time and max overshoot.
The bottom magnet is the inertial frame, while the top magnet is the body frame.